So now I think we are getting closer to the interesting algorithms and the reasoning tasks that we have to solve with this. So let's say I give you, so there are two tasks that we will study. One is called model finding and one is called deduction. Model finding says, I give you a knowledge base, I give you a new problem, tell me if there is a model for KB and S, which basically means S, the new problem, is consistent with the original knowledge base. This is sort of like constraint satisfaction, and we'll show you examples. Whereas deduction says, I have given you a knowledge base, I have given you a new question S, can you prove S from knowledge base KB? Is it true? And of course, if I want to prove S from KB, then either I can use some rules to derive new formula and finally get to S, or I can show that KB and not S is unsatisfiable. When do I ever show KB and not S unsatisfiable? Have you ever done this, that you have to prove something but you said not S and then showed that this is not possible? When do you do this? Proof by contradiction. So this style of proving KB and not S unsatisfiable is equivalent to mimicking proof by contradiction. Okay? So now we are getting closer to our first inference algorithm. Now what is an inference algorithm? It's a mechanical process for computing new sentences, and we will study three of them: backward and forward chaining, resolution, which is equivalent to proof by contradiction, and three, satisfiability problem, which is equivalent to model checking, model finding. So let us look at the very first simple inference procedure, and that is called the forward checking procedure. Now forward checking is based on the rule of modus ponens. The modus ponens basically says, if I know P1 and P2 and Pn imply Q, and I also know that P1 is true, P2 is true, and Pn is true, then I can prove Q to be true. That's as simple a rule as that. A and B, comma A implies B. A implies B and A entails B. This is how you will accurately say it in the language of logic, that in any world in which A implies B and A is true, then B is true. Now this rule, if you apply appropriately and prove new things, this is called forward chaining. I am starting with what I know and using this rule to prove new things in the forward direction. There is always a backward version of things, like you had forward search, you had backward search, and then you had bidirectional search. In the same way, backward chaining says that there is something I need to prove. Now let me see what thing should I have had in my knowledge base to be able to prove it, and then let me see how I can prove these things, and I keep going back, and that is called backward chaining. Anyway, if I only do modus ponens in the forward direction, would it be a sound procedure? Whenever I apply modus ponens and prove a new thing, will it actually be entailed? Come on, this is not a very hard question. So the question is, if this is the only rule I was applying, that whenever I know P1 to Pn, and I also know that P1 to Pn implies Q, and therefore based on this knowledge I prove that Q is true, will Q really be true? Yes. So will it be a sound algorithm? Yes, it will never say something which is incorrect. Will it be a complete algorithm? Will it be able to prove everything that is true? Can you give me an example? It will take you some time to think about it, but I will give you a simple example. Can you use this procedure to prove that nothing entails Q or not Q? Is this true? Yes. I don't need anything to prove Q or not Q. It's a tautology. But can I use forward checking to prove it? Forward chaining to prove it? No. Because forward chaining only applies modus ponens, and this rule cannot be proved by modus ponens. However, we know that if KB only has Horn clauses and query is a single literal, then forward checking is also complete. Here is the importance of horn clauses. And in fact, not only is it complete, it runs linear in the size of the knowledge base. Let's look at this example, and I think that will be the last thing we will do today. So suppose these are the things I know in my knowledge base. P implies Q, and L and M implies P, B and L implies M, A and P implies L, A and B implies L, A is true, B is true. And now I ask the question, is Q true? So what I can do is I can convert this particular knowledge base into a graph. So here every node is a variable, a proposition. Then I also know that A and B implies L. So the way I represent it is I take it an arc out from A, an arc out from B, and put it in this intermediate node. And I make an arc which says two of these things need to be true for me to get to L, and I make an arc from this dot to L. So basically what I am doing, I am keeping track of how many incident variables do I have in the antecedent. Antecedent is A and V, and what can I prove from it? That is the consequent. And I create this graph structure. And now what I do, I put A and B in my queue, because those are the two things I know to be true. Now I can run a simple forward checking algorithm. How can I run a simple forward checking algorithm? Because A is true, I pop it out from the queue, and what do I do from there? As soon as I know A is true, I know that the dot for A and B, the node for A and B, no longer needs two things to be true, it only needs one more thing to be true. So the antecedent has already got one thing satisfied. Okay, then I pop B, and as soon as I pop B, now I know that I don't need to satisfy both the things of this antecedent are satisfied. Because both the things of this antecedent are satisfied, now I can prove L. Because I can prove L, I put it in the queue. And I repeat this process. So now that I know L, I have put it in the queue, I pop it from the queue, and now I send the messages out saying, I have been proven, now you check for yourself. So now this other node which represented B and L now has been satisfied. That means I have been able to prove M. Because I have been able to prove M, I put M into the queue, and so on and so forth. I keep running this procedure, and at some point I get to Q to be true, and when I can get Q to be true, that means I have solved the question I had at hand. So now you see that this is an inference procedure which is using a mechanical process for computing new sentences. And in this case, if all the sentences are horn clauses of the form A and B and C and D implies something, and my query is a single variable or a conjunction of multiple variables, but not a disjunction. So if my query is a single variable, then I can say that this procedure is guaranteed to prove it, and it will be also complete. Okay. I think this is a good point to stop. We have to talk about two other inference procedures. One is resolution and one is satisfiability. But before we finish, here's a homework for you. I want you to read about what is a CNF clause and how do you convert any given clause into a CNF clause. Okay? We will start from there in the next class, and we will work up to the other algorithms. Thank you.